Okay, so conservation of momentum and energy. All right, so it says right here. When we're looking at collisions today and looking at the transfer of energy and looking to see if momentum is conserved or not conserved. So not in all cases will momentum be conserved. And we're going to look at those situations. So anyway, you're looking at your collision as far as the energy that they have and the momentum that they have before a collision, and then what they have after the collision and how they compare to each other. So it says when the bumper cars collide, F1 equals negative F2, which goes back to your Newton's third law. All right, equal and opposite. So for every action, there's an equal and opposite reaction. If you push on something, it pushes back on you with the same amount of force, but in the opposite direction, right? Okay, so that's going to be your F1 equals negative F2. So F delta T, what is F delta T? That's your force times your change in time, which gives us what variable? From your last set of notes, force times the change in time gives you what? Impulse. Okay, so this is impulse. So since your force is exactly the same, just in opposite directions, and the time over which that force is exerted is going to be the same, right? Because the two things that are colliding are going to be in contact for the same amount of time, right? Then that means that their impulse is going to be the same, all right? And we also know that your impulse is equal to what? Momentum, your change in momentum. So that's where this comes in. So therefore, if your impulse is equal to your change in momentum and the impulse for both objects is going to be the same, therefore the change in momentum will be the same for both of them, okay? So change in momentum of one object is equal and opposite to the change in the momentum of the other object that goes to this. And what did this equation break down into? The momentum equation? Well, actually, this is change in momentum. So what is it? P final minus P initial, which is going to be, and your P breaks down into what? Momentum equals, what's the momentum equation?
Mass times velocity.
Mass times velocity. All right. All right, so total momentum is neither gained nor lost. It should be nor lost during collisions. Your momentum is going to be conserved. All right, so the law of conservation of momentum, as far as the equation that you have from the reference sheet that I gave you, I'm going to write it down as it is on the sheet that you have. Looks like this. It's M1 V1 plus M2 V2 initial equals M1 V1 plus M2 V2 final. All right, so the way that you're looking at this equation is it shows them moving separately. So we have momentum of the first object plus the momentum of the second object, the initial, that's before collision. After collision, momentum of the first object plus the momentum of the second object, okay, again, after the collision. So you will have collisions where they will hit each other and bounce off each other. Okay, that's called an elastic collision. That's what you're looking at here. You have other ones where they will, when they collide, they will stick together, all right? You can still use this equation for that, even if it's an inelastic collision, all right? So total momentum remains constant during collisions. The momentum lost by one object equals the momentum gained by the other object. And then you had this practice problem. So it says a 62 kilogram astronaut on a spacewalk tosses a 0.145 kilogram baseball at 26 meters per second out into space. With what speed does the astronaut recoil? So the first thing that you need to do is you need to make your list and be careful with your list as far as what is before and what is after. And also, since you're working with two objects, you decide which one is going to be object one. That means your M1 and V1s, and then you decide which one's going to be object two. It does not matter, okay? It doesn't matter. If in this case we have an astronaut and a baseball, I can make the astronaut one and the baseball the two, all the information for the baseball two, or I can make the astronaut two and the baseball one. You just need to make sure that both sides of your equation, you keep it the same, okay? So astronaut, in this case, is going to go ahead and label him as 1. So kilograms gives me what? What is that about the astronaut? Mass. M1 equals 62 kilograms. And then we have what? Tosses a 0.145 kilogram ball. baseball, M2 equals 0.145 at 26 meters per second out into space. With what speed does the astronaut recoil? Okay, so initially, when this is, the ball's being thrown out, does the ball and the astronaut, do they start out together or they start out separate? He's throwing the ball. So initially, are they together or separate? They are together, okay? So that means as far as your, let me see, you're gonna make a list, V1, I'm gonna put initial, V2 initial, and then we're going to have V1 final, and V2 final. All right, so initially, since they are starting out together, what happens is their initial velocity is going to be 0 meters per second. And then he's going to throw the baseball. He's going to let go of the baseball, then baseball is moving at what speed? 26 meters per second. Where does that go in this list? V2F? And then we are looking for what speed does the astronaut recoil? Okay, so that's what you're going to be looking for. So you're going to take this equation up here and you're going to fill in the parts. All right. So as I said, it started out together and they end up apart. Even though these are listed apart, okay, you can use this equation for everything. Okay, all of your collisions. So when I fill in the equation, we have where is V1 final? V1 final is here. Okay, I'm going to go ahead and manipulate it to get the V1 final by itself. I'm going to go ahead and separate these out so it's a little bit easier to tell what's going on. Let's go M1, V1 initial, plus M2, V2 initial, equals M1, V1 final, plus M2, V2 final. Okay, so again, the V1 final is what I'm looking for. I need to get that by itself, so what would I do first? Subtract this one from both sides. So I'm going to end up with M1 V1 initial plus M2 V2 initial minus M2 V2 final equals M1 V1 final. Divide all of it by M1. Okay. All right. And then you plug in your numbers. Okay, so if you look at this, we're going to simplify. What do we say? V1 initial is 0, so that's going to 0 out, right? M2, there's my V2 initial is also 0, so that's going to 0 out. So that means what I'm going to be left with is negative M2 V2 final over M1 equals V1 final. Okay, so going ahead and plugging in the numbers. V1 final equals negative 0.145 kilograms times V2 final over M1. And the answer comes out to be negative 0.0608 meters per second. Okay, now does it make sense that it's negative?
Yeah.
Yes, because it's recoiling. So the ball goes in one direction, he throws it, and he is going to be pushed backwards, right? So he's going to be moving the opposite direction. That is negative. But pay attention to the question. If you wrote this as the answer and you boxed it as is, you're going to lose partial credit for this because it's incorrect. So read carefully what it's asking about. What is the question asking for? What does it say it's solved for? Speed. Is speed scalar or vector? It's scalar. Does scalar have a sign on it? Because it has no direction. So it's asking for the magnitude only. So your answer is actually for this one. If it was asking for velocity, you would leave it alone. We need that negative sign for direction. But since it's saying speed only, that's magnitude only. So it's 0.0608 meters per second. Make sure to box your answer. Hold on. Moving it over. Is that better? Can y'all see that? No. How about that? Okay. Anyone need it? Okay, so I'm looking at the second problem. Gerald is a quarterback and Tyler is a defensive lineman. Gerard's mass, is 75 kilograms. I'm going to go ahead and make him mass 1. And he is at rest. What is that? What is the, which variable? Which one? V1 what? Tyler has a mass of 112 kilograms, and he's moving at 8.25 meters per second. What is that? Good. When he tackles Gerard by holding on while they fly through the air, with what speed will the two players move together after the collision? Is this a, so they're moving together, right? Okay, so when we do the V final, since they're moving together, are their velocities going to be different? So you don't need to do a V1 and a V2, just do V final. If they are moving together, their speeds are going to be the same, so just simplify it to a V final. Because V1 final is going to be equal to V2 final. All right? So going back to that equation, we have M1 V1 initial plus M2 V2 initial equals M1. Now, since they are moving together, again, it's going to be the same final velocity. I'm going to go ahead and combine their masses, so M1 plus M2 times a V final. Does everyone understand that? Okay. Do you need me to, okay, so break it down. All right, so over here, if I'm going to, they're going to have the same speed, right? So let's say, let me go ahead and write this side out. Actually, I'll go ahead and do that so I can show you. All right, so if I have M1, V, but it's not going to be a V1. It's just going to be V final, right? plus M2 V final. What happens when I simplify this? Can I take anything, can I take the V final out, factor it out? So what, can I? V final in both. So what's it going to change into?
Mass 1 plus mass 2 multiplied by V final.
Does everyone see that? Okay, so that's what's going to happen. We're going to have M1 V1 initial plus M2 V2 initial equals M1. That's where that comes from. And then we need to switch it around, so we're solving for V final. So VF equals what?
Mass 1 multiplied by velocity 1 plus 2 multiplied by velocity 2 initial divided by mass 1 plus mass 2 is equal to velocity final.
Okay, good. Does everyone see that?
Yeah.
All right. And then all you do is plug in your numbers. Okay, initial velocity is 0 for first player. M2 is 112 kilograms times, which way is he moving? Okay, 8.25 meters per second. And you are dividing by their combined masses. So 75 kilograms plus the 112 kilograms. And your answer is going to come out to be 4.94 meters per second. Any questions on this one? All right, let's go to the back. I'm not going to do all the back since one of them is a repeat, but I wanted to show you the one on kinetic energy. Up here, this is conceptual material that you need to know. Okay, so elastic and inelastic collisions, it's a summary of the concepts. So you have perfectly inelastic, elastic, and inelastic collisions. What you need to know about this is what is conserved, okay, and what is not conserved. So here what happens is if you have an elastic collision is where they are going to collide and bounce off each other, okay? Like a ball is elastic. If I throw it down, it's going to bounce right back up. If I take a piece of clay, on the other hand, and throw it down, what's it gonna do? It's going to stick to the table, right? That is not an elastic collision. That's an inelastic collision, all right? So inelastic collision, they stick together and move together. Elastic, they bounce off each other and continue to move in their own separate velocities, all right? So if you have an elastic collision, both your momentum and your kinetic energy will be conserved, okay? So make sure you know what is conserved. The things that are conserved, which means the numbers will not change. They will be the same before and after. The momentum, the initial momentum and the final momentum are going to be the same in the elastic collisions, all right? Same thing for your kinetic energy. The amount of energy you start with is going to be the amount of energy that you end with. On the other hand, if you have an inelastic equation, it doesn't matter, inelastic collision, it doesn't matter if it's perfectly inelastic or inelastic. The only thing that is going to be conserved is momentum, all right? So again, in an inelastic collision, what is conserved? Momentum only. Okay, in inelastic collisions, is kinetic energy conserved? No. In inelastic collisions, I'm trying to talk slow. In inelastic collisions instead of elastic. I know it's a little bit confusing. So inelastic, elastic collisions, is kinetic energy conserved? No. Is momentum conserved?
Yes.
Okay. For elastic collisions, is momentum conserved?
Yes.
Is kinetic energy conserved?
Yes.
All right. So make sure that you have those memorized. Don't forget those, all right? Elastic collisions, what's conserved?
Elastic momentum.
Momentum and kinetic energy. Inelastic collisions, what's conserved?
Momentum.
Momentum only.